Mind, Gilbert, me getting started. I'm expecting here fairly soon to get to the homework 7 exam 2 cut point. I'll let you know exactly where that is, and move straight ahead into homework 8 material. And once we have, I think, maybe a couple lectures of homework 8 under our belts, what I am going to do, I mentioned this in the syllabus, I'm going to send you off to do homework number 9 on your own, parallel flipped classroom mode. I'll give you enough background to go off and do homework 9. Obviously, I'll be available for questions, but it's a perfect topic. Mirrors and lenses is a perfect topic for that because a lot of the derivations are not important. It's a very workmanlike thing where you just kind of learn how to use the equations and then you'll get your answers. So basically, I'll go to homework 8 and then I'll lecture. Once I finish lecturing homework 8, I'll start with homework 10. So I expect we'll have 10 total homeworks. And homework 9 and 10, you'll kind of do them in parallel. Other thing I did want to mention is that I do need to leave a few minutes early today from class. I got to really run and get somewhere else. So I'll try to get to a good spot, and then I'm just basically going to run out the door. Okay? Okay. Any admin or logistical questions before I jump in? Okay, so let's talk about transformers. We talked about this. We had a primary circuit and a secondary circuit. They're not electrically connected because there's insulation on both wires, but because the two coils are intertwined like this, there can be flux exchange, which means that if you change the flux in the primary, the secondary catches it. So remember that even though it does no longer appear in the equation, flux change is central to its operation. Okay, so you need to change the flux all the time in the primary for there to be induced current in the secondary. Lenz's law and Faraday's law is the fundamental operation of this thing. So basically, if you want to always change the flux, you might send AC in because AC sloshes back and forth all the time. It's always changing. The magnetic field caused in the coil of the primary is always going to be changing, and so there's always a change in the flux caught by the secondary. So we get AC out as well. So the question is, if you want AC, why don't you just use the original AC input? Why would you want to get AC out if you can just use the original primary circuit? What's the secondary circuit you do for? So that's what we started looking at last time. And we found out that the EMF, the peak EMF, seen in the secondary is not necessarily exactly the same as the EMF sent to the primary. There's a factor by which it changes, and that is the ratio of the number of turns. You basically count catchers and pitchers. Okay, so the secondary coil is the number of coils in the secondary that's catching the flux. The NP, that's the number of turns in the primary, and that is how many senders of flux there are. And you can have some options to mess around with the EMF, one of which is a step-up transformer. So step-up refers to what happens with the EMF. The EMF is going to be greater in the secondary than in the primary. So we have basically more voltage. The way that you need to do this is just to put more catchers in the secondary than senders in the primary, and then you will get a step-up. You'll measure a larger voltage on the output side, the secondary side, than you send in on the primary side. Likewise, a step-down transformer, you see less EMF in the secondary than you sent into the primary. And that's because you have less catchers and more senders. Okay? So, it seems like we're kind of getting something for nothing. We can step up the voltage, step down the voltage. Remember, voltage is energy per charge. So it seems like we're basically having some kind of violation of energy conservation. However, I can assure you that the energy that is sent into the primary is all there in the secondary. And energy per time, let me remind you, we call that power. It's a generic term for energy per time. So what we must say is that P going in is P going out. Energy must all be accounted for, or in this case, energy per time. So in this case, the power sent into the primary is equal to the power output of the secondary. that's our energy conservation. We have to make sure it's all there. So, how can we characterize the energy input? Well, here's what I will suggest. I will suggest to multiply the current times the EMF. And let me try to convince you that that would be a suitable characterization of the energy per time. Remember what current is, that's charge per time. And then EMF, well, that's measured in volts. What's volts? That's energy per charge. Okay? So we're multiplying how much energy each charge has by how many charges we have per time. You can see that the charge is just the middleman for the energy transport. You get energy per time. Okay? So we can characterize the total energy transport by multiplying the current by the EMF. How much charge flows per time and how much energy does each of those charges have. Okay? Now, if this looks familiar, it looks a lot like this. This was one of our equations for power dissipation in a resistor, right? That was one of the three forms. It's pretty much the same deal. This was charge that flows per time through a resistor. And then the V was, of course, the voltage drop across the resistor. So since the voltage was dropping, this was energy lost per charge. So same deal. This gave us the energy lost per time, which we call the power dissipated. So in that case, we were transporting energy from electrical form into thermal energy. So when we say it's quote-unquote lost, we of course just mean we didn't destroy it. We sent it from electrical into thermal, right? Now in this case, we're not losing it to thermal, we're just passing it forward, okay? So this is not energy lost, it's just the energy contained, okay? So we have a bunch of charge carriers in the primary all sloshing around, and I in the primary characterizes the charge flow per time, and then this characterizes the energy per charge, and it is constant. Remember, there's no resistance in here to the extent that this is an ideal wire. This whole coil, this whole primary coil is at one constant. There's no part of it that's at a different EMF than any other part, okay? So what I'm going to say here is that if we have to have that the energy is all accounted for, then the multiplying these two on the primary side should produce the same result as multiplying it on the secondary side. Okay? So that means that the energy is all accounted for. So now we can start to understand how it is that we're not getting something for nothing. The step-up transformer, you step up the voltage, so the voltage is higher, but the current is lower. Okay? So when you're stepping up the voltage, that's what step up and step down refer to. It's the EMF. Okay? This, you're increasing the energy per charge. Right? But something that has to give, you've decreased the charge per time. So you've gone to a larger EMF and a smaller current. So how is it that you have more EMF, more energy per charge, you have less charges? Okay? What you've done is you've entrusted the energy that's being carried forward. You've given a lot of energy to very few charges. Okay? So a lot of energy per charge to just a few charges. Okay? So this is kind of the capitalist direction, step up. Okay? Right? So we've taken all the money and given it to very few people, right? So the energy is all still there, okay? It's just that we have taken it and redistributed the wealth with giving a lot of the energy to very few of the charge carriers. So you'll find that the energy is all still there, but it's been transformed. Hence the name of this device is transformer. Okay? Let's do the step down transformer. Well, it's exactly the opposite. This is the step up referring to the voltage. In the step down, it's exactly the opposite. You go to lower voltage, higher current. So again, you've transformed how the energy is carried. You've given a little energy per charge to a lot of charges. Okay? It's redistributing the wealth. Okay? This is called the communist direction. Again, not making any value judgments on any particular form of government. This is just an analogy. Okay? So, it's a nice little parlor trick, right? That you can take the energy and kind of redistribute it. It's all still there. But you can basically have the freedom to shuffle around how much do you want each charge to have and how many charges do you have. Okay? So for instance, let's say this was a step-up transformer. Then if we have a bunch of charges all flowing around in the primary, the step-up will take the same amount of energy and give them to a few fat cats over here. Okay? So these will be sloshing around. Okay? And I've drawn them as bigger charges to represent the fatness of the fat cat charges with all the energy. Okay? They don't really get bigger. Okay? So this is a nice little parlor trick. You might ask, well, what possible purpose would this serve? You get, yes, it's possible to do this, but why would you want to do this? Well, let's talk about this. So here we have a power plant. Let's say it's, fossil fuel burning. And you want to get that energy all the way to your house or, a city, okay? Where there's a lot of houses. So how are you going to do that? You have to connect the power line. So we draw a nice power line here, and of course the thing has resistance this whole way, but just for representative purposes, I'm going to indicate it's not like there's a big resistor sitting in the middle of the power line, but the power line is resistive, right? It's made out of some material that's not a superconductor, so it has resistance. And it's going to take some of the energy that was generated and dump it out to heat, and so that's kind of a waste, right? You don't want to waste too much energy. Now, as far as the power loss here, I'm going to use I squared R as my formula of choice. And the reason why is because I want to avoid the voltage. The voltage is going to continuously drop from one end to the other, right? So we're going to go from here to here. We're going to get a voltage is going to drop progressively. So it's easier for me to talk about current because we know that once some current goes in one end, it's coming out the other end, right? That's the beauty of series. You can think of this whole thing as a chain of series resistances. The voltage is dropping, 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 but we can be sure that the current going in one end is coming out the other. And the amount of power loss we will get has to do with the total resistance in the wire from beginning to end, right? So we obviously want to minimize this power loss because guess who pays for it if you don't have all the energy arriving at the destination that you sent in the beginning? The consumer's paying for it, right? So let's talk about strategies. We've got two terms to work with. We can minimize the resistance, or we can minimize the current. Okay? So let's see what we can do about each one. So let's say we try to minimize the resistance. Well, resistance, just to remind you, here are the things that go into it. The material, resistivity, the length of the wire, and the cross-sectional area. So let's start with the easiest one, material. What do I want to do to the resistivity if I want to lower my resistance? Make it smaller, right? So what might prevent me from making it as low as I possibly want? Materials you can't just wish it, right? You have to make it out of some material, and that material, you're at the mercy of whatever resistivity there is. Now, you can get to be a superconductor where the resistivity is 0, but you can't do that at room temperature, so that's off the board. But you certainly would want to make your power lines out of some low resistivity material, like some metal, not like something higher, right? Something like plastic. That wouldn't make any sense. So you can lower that, but your material is limiting, right? Okay, so let's go to the area term. If I want to make my resistance as low as possible, what should I do to the cross-sectional area? Make it bigger, right? What might be a limiting factor or a reason why you might not want to make your power lines as large a cross-sectional area as possible? Block out the sun, too expensive, dangerous, right? So here, at some point, it's going to be too big. So you're limited there. And finally, if we want to make the resistance as small as possible, what should we do with the length?
Shorten it.
We want to make it shorter. Okay, so what's the problem with that one? That's probably the most obvious one. It won't reach, yeah. Okay. So you might think you only can do so much with these three factors, right? So you might think that this is a losing battle, but nonetheless, this approach was advocated by Thomas Edison. And his response was, well, I have such and such a material on hand. I'm not going to make the cross-sectional area bigger than a certain amount, so what I'm just going to do is just make sure the lengths are short. So everyone's just going to have a power plant about no more than 10 miles from your house. Because if it was more than that, the length would be too long, and you'd lose too much energy in transit for it to not even be worth it anymore. Okay? So he advocated having a power plant really close to everybody, send the electricity at extremely high voltage, such that when it dropped over the course of the power line, there was still enough left to use at the end, right? So you have 100 volts, and then you drop all this voltage, Ohm's law, and you get, maybe it gets 10 volts at the end or something, right? You lose most of the voltage. It is dangerous. You guys already learned what can happen if the voltage is high enough. Well, that can cause a large enough electric field to have dielectric breakdown, right? So these power lines, which were installed, this was first in New York City, where it's liable for most technology advances and will get first implemented somewhere like that. The power lines are such high voltage that they would regularly arc and come off of the wires and go where they weren't supposed to. So as the story goes, they had the subway cars wired like this, and people would just be walking along the tracks trying to get to their train and get blasted because there was such high voltage in the wires, it would just arc away with dielectric breakdown. So the people in this neighborhood got the nickname Dodgers because they would be dodging these things. Hence, Brooklyn Dodgers got their name. Now they moved, but that's supposedly where the name came from. Okay. So, there's only so much you can do with this. But if we could just figure out how to get the current down to a very low level, that would be awesome. Well, we just came up with a device that does that, the transformer. Okay? So the transformer allows you to trade, you're carrying the exact same energy forward, but you can trade how it's carried. So you can use a step-up transformer at the beginning here. Remember that this does not destroy any energy. This just transforms how it's carried. And you can take this power line and step it up to the kilovolt range. Why are you stepping it up to high voltage? Why are there high voltage power lines? Because high voltage is low current. Okay? So what you have is a transformer can help you go to high voltage and low current. This I'll call the Tesla approach. Okay? So you step it up to high voltage of kilovolts, but because you have such low current, the power loss that you experience, and by the way, the voltage drop you experience when you have a low current, it's still kilovolts out here. So you really haven't dropped a lot of voltage. Okay? By minimizing the current, you're going to minimize your power losses, you're going to minimize your voltage drop. So you send it in at kilovolts, it's still kilovolts on the way out. Okay? So, just to give you a little bit of the background on this thing, Edison, the reason why he wanted to take this approach is because he was advocating DC. Okay? So current that only goes one way, the kind of current that we spent most of this course talking about. The reason he wanted to have that kind of current is because he did not have a strong background in mathematics or science, really. He was kind of more of a perspiration kind of guy, right? His invention of the light bulb, it was like his 120th prototype. He was just trying stuff, okay? And at this point, it was also when we were electrifying America, he was also very famous at this point, had a lot of clout, but his knowledge of electricity did not extend much farther than yours is currently, okay? So along comes Tesla. Now, Tesla was nobody, came to the United States, said, Edison, can I work for you? And finally begged him for a job, brought on this awesome suggestion, and Edison said, that's stupid. And so Tesla left and he got his own backers. Now, of course, the transformer, even though we've eliminated it from the equation at this point, remember that flux change is crucial to this. If you don't change your flux by constantly changing the current on this side, you're not going to get constant output, right? It's the flux change over time that makes this thing even work. So this is advocating AC. Now we've just touched the tip of the iceberg with AC in this class, just a little tiny bit, but AC, while it's harder to work with mathematically, it has many, many advantages, okay? So, which one won out? Well, there was what's called the war of the currents first, okay? So there was a period of time where these two guys were really at each other's throats, okay? So Edison had a lot of clout already. Tesla ultimately had the better idea. So they both had kind of things going for them, and then it was just a war of the public perception. So Edison was trying to convince everyone that Tesla's AC electricity was so dangerous, he, among other things, invented the electric chair to electrocute. The first prisoner ever electrocuted was electrocuted with AC. That's because Edison was trying to show how lethal it was, okay? But the thing is, they both can be very dangerous, especially in the quantities that we use them today. It's just a matter of doing so safely, okay? But the real tiebreaker was that if you minimize the current freely with a transformer, this power line did not have to be a maximum of 10 miles long. It could be hundreds and hundreds and hundreds of miles, okay? So this led, using AC electricity, which along with it allows you to use transformers, allows you to transport electricity extremely low loss, hundreds of miles. So the electricity can be transported over a long, long ways. And the biggest triumph of Tesla's electricity was that they set up a generator at Niagara Falls, and then I don't remember where in Buffalo, but somewhere quite a ways away, the electricity arrived. So that was kind of the nail in the coffin of a DC. Okay. Now, ironically, solar panels produce DC, so DC is not going to go away completely. But our modern electricity grid is AC when you plug in something to a two-pronged outlet. It's a AC signal that's basically 120 volts at its highest, but sloshes back and forth. Okay. And who knows where you're getting your electricity at any given moment. There's an electricity grid where there's a bunch of different places where electricity is made, a bunch of different places where it's consumed, and the electricity grid just distributes freely based on need. Okay? So what happens here is that electricity is produced with a generator. It is stepped up in anticipation of long distance journey. The power line